particular PPT. So now, firstly, what is layout design? So first, we'll try to understand what is meant by layout design and how that layout design helps in designing an integrated circuit. So layout design is a schematic part of an integrated circuit, which mainly helps in extracting some data which is being given in the circuit design, so that this data can be helpful in order to design and manufacture an integrated circuit. And it also tells about how a particular component has to be placed exactly in order to go for the fabrication process. So if you want to go for the fabrication process, each and every component has to be placed in a correct manner, so that there will be no any kind of errors will be occurred, like parasitics will be occurred, and we should even look about the delays which occur while placing these components. So in order to overcome all these kinds of errors or glitches, we should be very much careful as a layout design engineers how to place a particular component and what is meant by floor planning and how routing has to be done. Routing means we are talking about, as I discussed in the previous lecture, it is about the connections between each and every component. That is about the routing. So in later classes, we'll study about in detail about what is meant by placement, what is meant by routing, and what is meant by this one floor planning. Okay, the next one. In this layout design, rules are to be described. Why do we need to describe the rules? This layout design rules will describe us about the smallest features. I'm talking about smallest feature means it talks about what should be the length of that particular transistor and how that particular transistor has to be connected, and what should be the width of this transistor. If I'm talking about the length, it means that I'm talking about the channel length. I'm talking about the distance or the between the source and drain. Why do we need to talk about the distance between the source and drain, or the length between the source and drain, which is called as a channel? Why? Because if you don't have any kind of channel between the source and drain, you cannot expect the charge carriers to move from one terminal to another terminal. So what does this? How does this charge carriers helps us in passing through this channel? Movement of the charge carriers is nothing else but you're talking about the movement of the signal, how the signal moves from one end of the terminal to another end of the terminal. If the signal moves from one terminal to another terminal, then only we can say that an input has been moved, or it has passed from the input terminal to output terminal. So if you don't have any kind of channel, then definitely we cannot expect that to get an output, even though if you supply the input at the input part. So that's why this layout design rules are very important. Layout design rules are very important to describe about the smallest features, and can be how closely they can be packed in a manufacturing process. Talking about the closely packed, if you're talking about the closely packed, means we are talking about the scaling part of these devices. Scaling means in earlier days we used to have manufacturing, I hope from 10 years back, they used to work, or the students used to study on softwares, EDA tools, which used to run on like 1.2 micrometer technology. But right now students are nearly working on 65 nanometer technology and also 45 nanometer technology. You can imagine what is how much it has been scaled. Means the size of the device has been scaled from the micrometer technology to nanometer technology. Probably most of the students in their colleges, they might be working with the 180 nanometer or 130. If you have got cadence, some of the colleges, they are offering nearly 180, 90, 45, and some they are even working with the 45 nanometer technology with the cadence tool. And some of the colleges are offering, like if you are having the mental graphics software. Mental graphics software has recently, which I worked with the mental graphics, it was with 130 nanometer technology. So 130 nanometer technology was the latest technology which I worked on mental graphics. So that's a difference between how the device has to be scaled. So if you are trying to scale the device, definitely there will be the more complexity you are supposed to encounter while designing the any kind of design. So you should be very much careful while designing any kind of a schematic design and then converting it into layout. So as a layout engineers, they should be very much careful with this smallest features. That is a WBL ratio, and they even call it as an aspect ratio. So that's why whenever you talk about manufacturing, then it comes with respect to the routing, placement, and even floor planning. It's like, see, if a smallest area of real estate land has been given to you, then you should think about how efficiently you can use that particular land in order to convert into a beautiful house, with all kinds of commodities and with all kind of whatever the requirements a particular house should have. So in the same way, a layout engineer also should think that if a small piece of die has been given to you, then how efficiently you can use that die in order to accommodate large number of transistors which are placed in different designs, which are to be converted into integrated circuit. As I talked in the previous lectures, that integrated circuits nowadays they are using some nearly millions of transistors in one smallest integrated circuit. So now it's hardly the size of an integrated circuit will be 1 micrometer to 1 micrometer. You can imagine how small. In that smallest area, you should try to fit large number of transistors, and also you should take care about how those transistors are to be placed and where it has to be placed, so that minimum layers can be used, and minimum glitches will encounter. And while in the process of this layout design, you can even remove the glitches, and you should think about all these things. So that's why they have spoke here about small features and their manufacturing process. So coming to this point now, why do we need layout design rules? Wow. So in this topic, we'll try to study about what is the importance of this layout design rules. So firstly, the layout design rules are very much used in order to specify in terms of microns. As we have discussed that there are two different types of layout design rules. Like one is in the micron design rule, other one is a lambda based rule. So industrial design rules are generally specified in microns, and this make to migrate one process to another process. See, if you're trying to use like 180 nanometer, and if you want to convert that layout into 90 nanometer, the same design can be migrated from 180 nanometer technology to 90 nanometer. So it will be easy for the software to adjust that micron technology or lambda based technology to move from one technology to another technology. That's the main reason why they use this layout design rules. So layout design rules, while teaching you about the layout, I have spoke about what should be the length of the P diffusion and what should be the length of the N diffusion. So all this width, length, all talks about the layout design rules. So now this layout design rules will help us to migrate from one process to more advanced process. Difficult because not all rules scale in the same way. So that's why this layout design rules are mainly used for migration. So it eases the technology process to move from one technology to another technology. So next one. So now, then again, as the days went on, then now we are trying to use this lambda-based rules on a single parameter that's called as a lambda, and that has been known by Mead and Conway lambda-based rules. And lambda, what does this lambda actually is? This lambda is nothing else but it's a resolution process, which is almost the half of the length of a particular or the aspect ratio of this particular transistor. So now here the lambda characterizes the resolution of the process, and is generally it's a half of the minimum drawn transistor channel length. So if you say that if it is like 180 nanometer you're using, so it will be 180 nanometer is the minimum technology, and it will the half of that one will be the lambda based rule. So that's how the software will be considering the particular design rules, and it will try to migrate from one technology to another technology. So now the channel length is a distance, as I spoke anyway, it's a distance between the source and the drain. So now the minimum width of this one can be set with the help of this lambda. And the channel is nothing else but it is a distance between the source and drain, which is set by minimum width of the polysilicon wire. So now we use the polysilicon wire has a which runs perpendicular to the diffusion layer. So now once if the polysilicon has been run perpendicular to the diffusion layer, we call that one as a transistor. So now this channel length, and one example also you can see here now. If I'm talking about 180 nanometer technology, then the lambda rules which the particular software will be using is that it converts it into 90 nanometer technology. So now the lambda will be of 90 nanometer. So that's how the software will be migrating from one technology to another technology, and it will be easy for that for a design engineer to switch from one technology to another technology by using this lambda based rules. So these are regarding some examples like how the same layout can be moved to new process. That means I'm talking about from 180 to 65 or 65 to 45 or 90 or 130 nanometer. So it will be easy for us to migrate from one to another technology. So that's why the same layout can be moved to a new process simply by specifying the lambda value. If you can specify the lambda value, you can easily, by using this lambda value, you can migrate from one technology to another technology. So now the potential density advantage of Microwind rule is sacrificed for simplicity and easy scalability of the lambda rules. So now here, when you talk about the why we have been migrated, or why we are mostly using lambda rules than compared to the Microwind rules, because when you talk about the Microwind rules here, the density, potential density is very important. It talks about the denser nature of the devices. So now if that can be minimized with the help of this lambda rule. So that's why they have sacrificed that one, and they have gone for the simplicity. That's a simple way of using the design rules with the help of lambda rules. And while discussing about design rules, I spoke that different technology will be having different features and different what to say, lambda values for different layers, I have told. So that's what this talks about. Designers often describe a process by its feature size. So see, this feature size is very important. While designing any kind of a circuit, we should be very much familiar with the feature size. We should make a paperwork before going to the designing part. That's analog VLSI. We call it about the analog VLSI. You should try to design that particular transistor very carefully, that what should be its length and what has to be its width. And all those things you can find it in a Razavi book, Analog VLSI Design Razavi book. It explains very clearly how we are supposed to start the designing of a any kind of design, like any kind of op amp or any kind of transconductance op amps. Different kinds of op amps and different kinds of digital circuits have been given there. You can look into that one, how each and every transistor has to be designed, and how we should take care about VGS value, that's a gate and source voltage. All those things are very important while designing this particular process, and also to specify what should be the feature size. That's I'm talking about the width and length of the particular transistor. So feature size here, which refers to the minimum transistor length. So lambda is half of the feature size. Just now, as I told, 180 nanometer means the length is like it talks about length, it's 180 nanometer, and then lambda will be of 90 nanometer. That's the feature size. And the other name for the feature size, it can also be called as an WBL ratio, or else it is also called as an aspect ratio. The other name for the feature size is WBL ratio, or else it is also called as an aspect ratio. So another examples have been given regarding that feature size. This is regarding, so see now, in digital systems, transistors are chosen to have minimum possible length because the short channels will be more faster, smaller, and consume lesser power. So see now, we try to design this one, any kind of transistor, the length between the channel length between the source and drain has to be very small in order to get an what to say, faster output. If the channel length is very small, then definitely the signal can move from the one end of the terminal to another end of the terminal very easily. So that's why and digital systems are very faster. So it has to be a smaller channel length. Because of this shorter channel transistors only, digital systems are faster, and they also consumes lesser power. If the signal is taking longer time to move from input part to output part, definitely it consumes the power during that entire duration of its motion from one end of input terminal to output terminal. So that also has to be taken care. The CMOS technology is mainly regarding the lesser power consumption. So we should try to design the circuit in such a way that the channel has to be very short, so that a signal can move very fastly from one end of the transistor to one end of the terminal to another end of the terminal. That's the input terminal to output terminal. And here we can see now, these are the different kinds of layers. You can see the between metal and metal, metal 1 and metal 1, the spacing should be 4 lambda. Means if you try to put with lesser than 4 lambda, then definitely it shows some error in that while you go for simulation part of that particular layout. If you try to simulate the layout without this what are the lambda rules have been given, then definitely error will be occurred, and that error has to be again we should remove that error, and we should again re-simulate that particular layer. So these are the main rules, basic rules which are to be used in order to design any kind of layer. Between for the metal one, as I told that 4 lambda is a 4 lambda, that's a WBL ratio. Width should be 4 lambda, and also the spacing between the two metal one layers should be 4 lambda, and even it's the same with the metal 2 also. And when it comes to the diffusion, even in the diffusion, we have drawn the P diffusion and N diffusion with the help of same these rules only. We have taken the width of the P diffusion and also N diffusion of 4 lambda, and between each and every diffusion, there should be minimum spacing should be of 4 lambda. And for the polysilicon also, we have drawn the polysilicon for the inverter by using the same 2 lambda width, and also the spacing between the two polysilicons. The spacing between the two polysilicons means we are talking about the gate terminals. The gate terminal polysilicon actually it refers to the gate terminal. So now between these two polysilicon, the spacing has to be 3 lambda. And down you can see that you can see the different kinds of contact cuts have been given here. The first one is a contact cut, is a metal one and diffusion contact cut. So now we have used this metal one and diffusion contact cut while drawing the source terminal and drain terminal upon the P diffusion and also N diffusion. Whenever you are using a metal upon this P diffusion or N diffusion, we should use a specific contact that with respect to P diffusion, you'll be having a P diffusion and metal contact, and also with respect to N diffusion, we have in the software by N diffusion and metal contact. So we are supposed to use an appropriate contact, and that contact which should be of 1 lambda, and the spacing between the two contacts. So you see the other one, another contact is also been given. That's the metal one and polysilicon contact. For even polysilicon, we should use an appropriate contact which is of metal one and polysilicon contact. So again, the spacing between the two contacts has to be it is given right between from 1 lambda to 2 lambda. So that this kind of spacing we are supposed to we should maintain. And even you can see in between metal 1 and metal 2. See, as I told that there are different kinds of metal layers with respect to different EDA tools, and for basically you'll be having two metal minimum of 2 to 3 metal layers. So first one is a metal 1 and metal 2. The contact between the first metal and metal 2, it should be like 3 lambda has to be used between the two metals. That is a minimum feature for lambda based rule, that's between two contacts of metal 1 and metal 2. So let us see some few basics about stick diagrams and stick diagram. So stick diagram, we know that it is a main which acts as a cartoon of the layout, which will be used for conveying the layer information by using the color codes. We'll be using a color codes like we have studied that P diffusion will be of a brown color or yellow color, and then N diffusion will be of a green, and polysilicon is of a red color, and metal is of a blue color. So these are the color codes. So these stick diagrams are mainly used to convey the layer information through the use of color codes. So you can see the examples there. The green color is used for N diffusion. Red is used for polysilicon, blue for the metal, and black for the contact areas. So these are the main thing regarding the stick diagram. Stick diagram is a stick figure view of a layout. It is useful for planning a layout. First, in order to go before looking into what is meant by layout, we should draw the stick diagram and then convert or that particular stick diagram into layout. So why do we need this stick diagram? The stick diagram is mainly used for planning the layout and for the placement, how the transistors has to be placed, and also for assigning the signals to the layers. It means you are talking about input signal, where the input signal has to be assigned and where the output has to be obtained, and where the VDD and ground has to be assigned, and connections between the different cells, and also for the hierarchy of the cell. So this is the main reason why do we use the stick diagrams. And these are the few layers of the stick diagrams. You can see color codes for the green. For the N diffusion, we'll be using the green color. For red is used for polysilicon. Blue is used for the metal layer. Contact cut is black is used, and for yellow color is used for like NMOS only, where we'll be using for implant also, and we'll be using even for the well, N well also we'll use the same color. So these are the few layers, and you can see the layout masking and also stick diagram masking of those different layers, which are mentioned in this particular figure. So this is regarding the stick diagram and layout encodings. And in this particular figure, we can see about yellow stick diagram here, which is used for the P diffusion here, and the masking has been done. Different kinds of masking, and metal layers, metal 1 and metal 2 layers have been used. Different kinds of contact cuts. You can see here how the VDD and ground contacts has to be done. If you're talking about the stick diagram, it has to be done with the help of black cross mark. If you're talking about the layout diagram, it has to be done in this fashion, which is given in this particular diagram. And also we can see the demarcation line. Demarcation line has to be drawn with the help of brown color. So this demarcation line is a line which will separate the P device from the N device. So the top one will be P structure and bottom one will be N structure. So these are the few types of sticks and stick diagram symbols and also layout symbols. It's an N type of enhancement mode of transistor. You can see that here 3 terminals. Whenever a gate terminal or a polysilicon runs perpendicular to the diffusion, then we call it as a transistor. So these are the 2 different types of notation how we can make. The first one is that it's a horizontal diffusion has been taken, and vertical polysilicon has been taken. That is a fashion of stick which we are used while drawing the CMOS inverter or Nand gates, Nand gate structures. And it's a other way. Second diagram, we can even try to draw the diffusion in the vertical one, and we can draw perpendicular to that polysilicon. And there's a symbol of layout and also stick. We can see that contact cuts where for the drain and source terminals. For the source and drain terminal, if you want to make that particular drain to get connected with the drain of another transistor or another terminal, then definitely we are supposed to use a contact cut, and that connection between the 2 transistors will be done with the help of metal layer. That's why we can see that blue color there. These are the few more type of sticks. I can see that well notation or implant notations there for that particular sticks, and also the layout. And this is talking about the P mask or the well which is used for the layout. So the rules, anyway, we have studied about the 4 different kinds of rules. Let us see again what are the 4 different kinds of rules here. When 2 or more sticks of the same type cross or touch each other, then it represents an electrical contact. Whenever the same type of sticks are crossing one upon the another or touch each other, we call it an electrical contact. That is the first rule. And second rule is that whenever the different kinds of sticks cross each other or touch each other, then definitely there will be no electrical contact. So in order to make an electrical contact, then we should use a kind of contact there in order to make it as an electrical contact. Then the third kind of rule, whenever a poly crosses a diffusion, it represents a transistor. So if you don't draw a polysilicon upon the diffusion, then we cannot call it as a transistor. In order to represent any kind of stick or a layout, a polysilicon is very important, which resembles the gate terminal in a transistor. So because if you don't have a polysilicon, then we cannot give any kind of input signal to that particular layout to generate any kind of output of that particular design. So polysilicon is very important. Polysilicon layer has to be drawn always perpendicular, which has to run perpendicularly upon the diffusions. Then the fourth kind of rule is that in CMOS, a demarcation line is drawn in order to avoid the touching of P diffusion with the N diffusion. So now all PMOS should lie on one side of the line and all NMOS should lie on the other side of the line. So the PMOS will be always above the NMOS. So the top one, the structure which is above the demarcation line is a P structure, and the structure which is below the demarcation line will be called as an N structure. So these are the different kinds of rules which you are seeing. The first one, you can see how it's a representation of different kind of sticks we can see now. See now, we have made here one contact. This indicates that here this particular these two are of two different kinds of layers. So that's why we have made a contact here in order to convert it into an electrical contact. In the same way, here also electrical contact has been done. Here, if you don't try to put an electrical contact, means either it should be of a similar kind of layers, so that the electrical contact will be already it will be done, or else if it is of if you don't want those two layers to represent any kind of electrical contact, simply you can draw one upon the another, so there will be no electrical contact. But if you are using two different kinds of layers and if you want an electrical contact, then definitely this electrical contact has to be done. So these are the different types of representation of stick diagrams. And see, this is the demarcation line. The demarcation line between the two transistors here. This top one indicates it's a P device, and this one indicates a N device. So it's a completely P module, which comprises of completely all types of P devices, which are present in a particular design, and also this is regarding the N type of devices. So this line will differentiate P device from an N device. So this is regarding the demarcation line. So these are different types of different two types of transistors we have studied in the initial lectures, like enhancement mode transistor and depletion mode transistor. If you are using an enhancement mode transistor, no need of using any kind of implant over here at these three terminals, at the juncture of these three terminals. But when we are trying to use a depletion mode transistor, we should use an implant here. This implant will notate that this particular design is of enhancement mode, whether it's of enhancement mode or depletion type of mode transistor. So this is how we will be differentiating enhancement mode and depletion mode transistors. So these are the regarding the depletion line, demarcation line for P transistor, P type enhancement mode transistors. And coming to the CMOS structure or the CMOS inverters, stick diagram and also layout. So here, this is a CMOS inverter. We know that it's a combination of PMOS and NMOS, and this is the input part and this is the output part. Since PMOS will be always generating a negation of an input or complement of an input, so that's why if input is X here, we'll be getting an X bar as an output. It means that if I try to input 1 here, logic 1, then the output will be logic 0. So that's the meaning of this X and X bar. And this diagram has been, this particular CMOS structure has been converted into a stick diagram here. The first one is a P diffusion, and for the P diffusion, we have drawn perpendicularly, we have drawn a polysilicon. And the second one is an N diffusion, which is in green color. And for this one, perpendicularly, we have drawn a polysilicon. And in the structure, you can see that both the gate terminals are connected here. So this is a gate terminal of PMOS and this is a gate terminal of NMOS. So since this both gate terminals are connected, so here in the stick diagram or the layout, the polysilicon will represent the gate terminal. So now we'll try to connect both the polysilicons here. When these two polysilicons are connected, then we can give an output here as an X. And also since here both the drain terminals are connected, the drain terminals are connected with the help of metal layer. So that's why we have used here this contact cut. Why? Because we are trying to join one type of layer with the another type of layer. We are trying to join, we are trying to make a connection between a metal layer and also P diffusion, and here it's a metal layer and the N diffusion. So these are of two different layers, and it cannot be made an electrical contact between the two different layers until and unless we put in contact with the help of a black color, which is in black color. So now this indicates an electrical contact has been done between the metal layer and also polysilicon, and here is a metal layer and the N diffusion. So now once this drain terminals have been connected, we can obtain an output at this part. And similarly, we can see here now, this is a power rail and this is also power rail. This indicates the VDD, the main supply, and this indicates the ground, which is a low supply, so which is almost equal to here in our case it's 0 voltage, and this is a high voltage. So now, since this power rails have been drawn with the help of metal layers, we can either drag the metal upon the this P diffusion, or else we can drag this P diffusion upon the metal layer. Anyone can be done, but wherever you are trying to make the connection, there you should put a contact in order to make them as an electrical contact. So now we have dragged the P diffusion upon this metal layer, so we have put a electrical contact here. In the similar fashion, N diffusion is dragged upon the metal layer, so we have put an electrical contact here. In order to make an electrical contact, we have put a contact here, which has been indicated with the help of black color. So this is regarding the layout structure. You can see this entire thing is a VDD, and this is a ground terminal, and this part is a P diffusion, and this is N diffusion, and this is a source terminal and drain terminal of the PMOS, and this is a drain terminal and source terminal of the NMOS. So you can see that here you can inside this one you can see one small darkened dot is that indicates the contact of this one, and here also you can see one small darkened dot that indicates the contact between this metal and also P diffusion. In similar fashion, it is a contact between N diffusion and the metal, and this is a contact between N diffusion and metal. And now both the polysilicons have been drawn here perpendicular to that one and made in connection, and input terminal has been given at this polysilicon, and output will be obtained from the drain terminal. So this is nothing else but the well. This is a well which has been drawn for the P diffusion. So we are used here N type of well in order to draw this layout diagram. And this is the diagram. I hope you all know this is for NAND gate. CMOS, this actually, in fact, it is for A dot B. We will draw it for A dot B, but when we try to realize this particular circuit, it is not an A dot B, which is of NAND gate, but this structure is for CMOS structure is for the NAND gate. So you can see here, this is a structure which we have learned about how to convert a Boolean equation into a CMOS structure. So for this one, actually, as per the Boolean equation y equal to A dot B, we are supposed to get this outputs for 0, 0, it will be 0, 0, 0, and 1. But once if you try to convert that Boolean equation into CMOS structure, we have seen that while realizing the circuit, we have seen that the output which we get will be 1, 1, 1, and 1. If you are supplying 0 and 0 as inputs over here, for here and here, this indicates, see that this indicates that A and A are connected and also B and B are connected. So whenever you try to supply input A as 0 and input B as 0, then we are supposed to get output as 0 if as per the Boolean equation, which is y equal to A dot B. But while realizing of that particular CMOS structure, we came to know that the truth table of the structure is very exactly different or exactly opposite to the A dot B. So then we have found that the output will be for 0, 0, whenever you input A equal to 0 and B equal to 0, we got output equal to 1. And for 0 and 1, we got 1 and 1 in the next cases, and also 0. So this is a CMOS structure for this NAND gate, CMOS NAND gate. And this is this entire diagram, CMOS structure can also be drawn in the form of a stick. And this is a stick diagram which we have used while drawing the CMOS structure of, while drawing the CMOS structure of NAND gate. So here you can see this is one PMOS, P1, P2, and N1 and N2. And both the polysilicons which acts as a gate terminals are connected here, and both the polysilicons of the P2 and the N2 are connected here. So here you'll be feeding the input A, and here we'll be feeding the input B. And ultimately we get an output at this part. And this cross mark indicates that electrical contacts, which are in black color. So this is the stick diagram for the CMOS NAND gate. And this is for the NOR gate, for CMOS NOR gate. NOR gate also we have even drawn the stick diagrams. So this is how this particular NOR gate looks like once if you try to draw the stick diagram of a NOR gate. This both are the P1 and P2 transistors, and this is N1 and N2 transistors. See here we can see that, see now. Here we have taken the input of this N2, polysilicon has been drawn up to here, and then we have not drawn the polysilicon upon this diffusion. We have used a metal layer. If you draw the polysilicon upon this diffusion, then again it becomes an error, because any diffusion will be having only one polysilicon which represents one complete transistor. If we cannot draw like two input transistors, we can even though there are two different kinds of structures which are used, but as per this particular design, we cannot draw this polysilicon again upon this one. So they have used a metal layer to make this connection. So metal has been drawn here, metal has been used between this polysilicon and this polysilicon, and a contact cut has been used here in order to make it as an electrical contact. But here, if you see at this particular part, no contact cut has been used. It means that there is no connection between this diffusion, this N diffusion and the metal contact. So this is how we are supposed to draw the stick diagrams or layouts very carefully by keeping every rule in mind. So this is a stick diagram of a CMOS NOR gate. And this is for one of the example. Example is given for the Boolean equation A dot B plus C whole bar. A dot B means it is regarding A dot B. For the dot operator, I have told that if it is a dot operator, the PMOS, how the PMOS are to be connected here, the PMOS will be in parallel. And then for this dot operator, there is another operator of input, that is plus C. So even how to recognize how many PMOS or how many NMOS we need, it depends upon the 2N, the number of transistors which you required for designing this one. It depends upon the number of variables which are given here. So here there are three variables. It means that we required 3 PMOS and also 3 NMOS. So that is equal to the total number of transistors which required in this particular design will be of 2N. So N represent the variable. So since we are having A, B, C, so we require 3 PMOS and 3 NMOS. So for this A dot B, 2 parallel PMOS are connected, and for this parallel structure of PMOS, there is a plus operator. Plus operator indicates that the PMOS should be in series. So for this P structure, the PMOS will be in series. In a similar fashion, when it goes to the N structure, for the dot operator, the NMOS should be in series, and for plus operator, NMOS will be in parallel to that N structure. So for dot operator, PMOS should be in parallel and NMOS will be in series. For plus operator, PMOS will be in series and NMOS will be in parallel. So that's why for the dot operator of NMOS, here A and B are in series, and since a plus operator is given, for this 2 AB transistors of N type, another N type transistor is been used as a parallel. So that's why we have drawn this one. And for the same structure, we should convert, or we should draw as a stick diagram. So this will be the stick diagram of this Boolean equation. This is one transistor, P1, P2, then again this is a P3 for the C input. This is input A, input B, C input, and this will be, like you can see here now, there are these are the transistors like N transistor, N1, N2, and N3. So now here, excuse me, now here this is a N1, this is N1, then again this is N2 and N3. So now since we can see that here input A is connected to N1, P1 will be always connected to N1, P2 will be connected to N2, and P3 will be connected to N3. So now these are three different PMOS and three different NMOS. So this becomes a complete stick diagram of an Boolean equation, which is given here. So now we have completed the particular presentation, and we'll try to look into the software. I hope we can complete. We have got still some 5 minutes of time. I'll try to show one design, how to draw that one, how to draw the I hope you all can see this particular software interface. Can you see this one? Can anyone respond to me? Can anyone respond to me?
No, sir, it's showing only. Thank you.
Okay, just a minute. I'll close that one. Yeah, can you see now?
Yes, sir.
Yeah, okay, fine. Thank you. So see now, this is a software. One part of Microwind software, as I spoke to you in previous lectures. Microwind is of two types, like one is a designing of a schematic software, other one is a layout designing. Exclusively, it is for one software is for designing part, and other one is for the layout design. I have put an official email for the Microwind people. In order to get the license of the Microwind, we have got a license for this schematic design, but I don't have the license for the Microwind software. I have put a mail. Probably within 1 or 2 days, we'll be getting the mail we'll get a license for that one. So first, we'll try to see about this one software. So this is the name of the software is called as an DSch. It's a design schematic software. This is design schematic software. You can see here, if you see the palettes here, this one is a file where you can open different kinds of any previously drawn this schematics, and we can save that one. Here you can see this Foundry. Here Foundry means it talks about the technology, in what kind of technology we are supposed to draw the particular file, and also we can make a Verilog file. I hope you are good at HDL software, HDL, hardware description language. As we know that there are VHDL and also Verilog is other part of the HDL. So we can even directly obtain the HDL code for the design which you are drawn here. And these are the few schema, new symbol like properties. We can use different properties. We can make it as a complete white color, as a monochrome color. And next, these are different types of edit, insert. We can insert any kind of symbols, user symbol which you have already saved. And these are the few shortcuts where cut is used for, if you don't want any kind of symbol here, we can use this cut gun symbol is being used. In order to remove that one, paste, copy, and rotating of the, in order to rotate left, right, and flip that transistor, we can use all these symbols here. So now directly I'll enter into the designing part. So now here we have got two types of palette. In this palette, we have got two different types of components here. In the basic component, we can see here, this is one which is used for inputting the signal. There's a ground terminal. This is the VDD supply, and this is a clock where we can use a completely pulse can be given here. And okay, fine, just a minute. This is how it comes here. clock signal, and this is a one which is used for obtaining the output, and this are the few more transistor hexadecimal designs also can be made as an output, and this is a inverter. One is a logical inverter. This is the 3-state inverter, different kinds of inverters, and buffer. This is a 3-state buffer, and this is for a 2-input AND gate. This is 3-input AND gate. This is a NAND gate, 2-input NAND gate, 3-input NAND gate, OR gate, NOR gate, 3-input NOR gate. So these are different kinds of logic structures which we can use here. And this is a NMOS transistor, and this is a PMOS transistor. If you enter into the advanced one, in this palette we can have a resistor, capacitor, inductor, different kinds of op-amp symbols are there, and we can even see a diode, and these are different kinds of components which we can use in order to make a design. So let's first, as a part of this one, we'll try to design one CMOS inverter, and we'll check how it works. So first, what I have done is that by using your mouse, sorry, by using your mouse, click on your left click and select your transistor and drag it onto this one. We should select and drag it, and since it is a PMOS, we know it's since it has got a bubble, we call it a PMOS, and now this is a NMOS. You can click that one and press your left click and directly drag onto the this particular software. And now, in order to make the connection between the PMOS and NMOS, we can use here, you can see here, line, add a line is there. This is used to make the connections between the PMOS and NMOS. And this we have made a connection between the drain terminals, 2 drain terminals. And now we know that as per the CMOS inverter, we should make a connection between the 2 gate terminals. So this is how we make a connection between 2 gate terminals. So I need to give one input to the input signal to the gate terminal. So I have made this connection of line which acts as a terminal, and this is for the output terminal. And now here we should supply the VDD. So I'll try to select the VDD from this palette, and by pressing the left click of the mouse, I'll drag it on this one and place it wherever I require that one. And similar way, this is the ground terminal. Press that one with the left click and drag onto this particular software. And similarly, we need an input signal. So here I try to take this this one will act as a button, will act as an input signal. So now press that one with the help of left click, drag onto the software, and we have made a connection here. This will supply the input to this CMOS inverter. And output here, this one light will act as an output for this one. So press that one and drag onto this one. So now we can even name this one. Parameter can also be named. Pin names. You can see here now. If you double click that one, if you double click, you can see the symbol title. You can see the PMOS, and in similar way, double click symbol title and NMOS, and we can even show that PMOS and NMOS source and drain terminals of this one. Source and drain terminals. Double click of the PMOS, show pin names, and also this one I'll put it. You can see now. This is the WBL ratio. What should be the width of this PMOS transistor and what should be the length of PMOS transistor. This entire thing works upon 1.2 micrometer technology. This software is one which is a student version which works on 1.2 micrometer technology. So the width of this particular transistor is this is the aspect ratio, which is default value 0.5 micrometer, and length is 0.05 micrometer. And in a similar fashion, we can even use name this one by selecting these pins. Show pin name, show symbol name, symbol title, and show names and proportions. So we can use this one. We can select all this one and click OK. Once if you select this one, it will be displayed. And we can even change the width and length of this transistor. You can see, excuse me. You can even change this one. See, we can even change this one. If you have designed any kind of design, if you have done a paperwork for designing the analog part of your CMOS design, and if you got any of the width value and length value, those values can be inputted in this length, channel width and channel length place, and we can click it OK. So those values can be obtained here. See here, if I change the name, you can see here, if I change some value, the width will be changed. Now it has become 0.3. So let me put it as a default one only, 0.5. In that way, we can give the width and length of this particular design. So now we have constructed our CMOS structure. So you can see here now the for the source of the PMOS will be always in the top. Okay, I'll add one so that it will be easier to understand. Okay, this is the source of this PMOS. This is a drain of a PMOS, and this one is a drain terminal of NMOS, and this is a source terminal of NMOS. So the gate terminals are here, gate of PMOS and gate of NMOS. Both the gates are connected, and see here, you can even see the difference between these two. This will act as an what is it? This will act as an metal layers which are used for drawing the gate terminals. So now let us make a simulation of this one. So you can use this one simulation button, run simulation. We can use. Click on the run simulation. And once if you click on the run simulation, it will pop up this particular simulation control window. Now we can give the inputs. If this light is seen here, means we have supplied some input, logical 1. Then remove that one, logical 0. Logical 1, whenever it's logical 1, this LED will not glow. It means that output is equal to 0. Okay, so now logical 1, we know that the PMOS will be turned off and NMOS will be turned on. So that's why you can see the channel has been off whenever between the source and drain. There is no channel. It is a switch off condition. So now here the channel has been created between source and drain. So now whenever logical 0, we know that for the CMOS, whenever it's logical 1, we know that the input of the CMOS inverter will be 0. So now if it's logical 1, sorry, it's a 0. Whenever you supply logic 0, the channel will be created between the source and drain of PMOS, and you can also see the channel is lost between the source and drain of NMOS. So this is how it works. The PMOS will be on whenever it's a logical 0 is supplied, and the NMOS will be off whenever it's logical 0. And whenever we supply logical 1 as an input, then PMOS will be turned off and NMOS will be turned on. So this is how a CMOS inverter will be working. So now I'm trying to give some inputs here. Logical 1, logical 0, logical 1, logical 0. So now once if you get this one, click on this button. There's a timing diagram. If you click on timing diagram, you can see the outputs here. See, whenever it's input is 1, the output will you can see 0. Okay, whenever the input is 0, output is equal to 1. So 0, 1, 1, 0. 1 input is 1, output is 0. So 1 logic 0 as an input, output will be 0. Sorry, output whenever it's 0, input is 0, output will be 1. So now here, since I have given inputs very fastly, so that's why we have seen this structure. You can see, you can even click that one. We can see the detailed part of this part also. You can click on this one. If you click on that particular one and click on this arrow, you can see it now. See, whenever we give input as 0, again we get an output to be 1. 1 is an input. If input is logic 1, then output will be logic 0. So this is how an CMOS inverter will be working. I hope you have understood this one. And then once if you have completed this one, I'll show now how to get the Verilog code of this particular structure. In the similar fashion, you can draw different kinds of structures, and you can even obtain the Verilog code. Go to file, make a Verilog file, and I hope you are familiar with the Verilog. If you see the syntax of Verilog, you'll be having a module, then module name will come, and inside that bracket you'll be giving input and output. There are again different styles of writing the Verilog code. first companies will be mostly in the companies they'll be using output will be written and then input will be written. But as per this we can use even there's no problem with writing as input or output. First module, then module name inverter, or example it has taken by default example. So input one only, we are having only one input and one output. So first is input and then output. And what is the input name? You should specify that among the signals which are given here, input one and input output one, you should specify which is input and which is output. So IN1 is an input. So input IN1, output out one. So this is how we should specify those signals which are mentioned in this particular bracket. Then again, wire, if you have used any kind of wires, then that particular wire will be used here. Connection, that's the interconnection between two different kinds of structures will be used. Then I hope you remember different kinds of descriptions, like we have got in HDL. We are having like data flow, behavioral, structural, switch level, mixed level. So these are different kinds of descriptions of writing VHDL program and also Verilog program. So now here they have used here switch level description has been used. This is a switch level description, PMOS, this slash, then again we can use one. First PMOS, we are having only one PMOS, so it is one is been used here. Hashtag one, then again PMOS one, the name of that one is PMOS one. First output, then write the inputs. Output one of the PMOS, then VDD is the one input to the PMOS at the source terminal, and gate terminal is input one. So you can even see the WBL ratio of this PMOS also. Then again NMOS. NMOS, only one NMOS is there. NMOS, then this is a second transistor, so NMOS 2. The naming, this is the naming of the transistors. Okay, anyway, we can name anything. Then again output one, that's a output one, that's a drain terminal where you get output of the NMOS, output one. The same one is same for both, the output is same. So that's why output one and output one. VSS is another signal at the ground terminal. And again, input one is the same input for both the transistors. So it is input one. And these are the WBL ratios of NMOS, end module. So end module. So this is how we get this Verilog code for any of the design which we work in DSch. Once if you get this one, we can save this one as an we can save the name as CMOS inverter. We can save it as CMOS inverter, and you can click OK. You will find this particular Verilog file in the file of this DSch. You can open that one in Microwind. We have got one provision in the Microwind that by using this, whatever the Verilog code we have created just now, we can use that Verilog code in the Microwind, and we can compile that Verilog code, and the software will generate the layout for that particular design which you have used up to now. Okay, so this is how this DSch will be working. So in the coming classes, we'll work upon this DSch and layout, and we'll try to design even for a CMOS NAND gate and NOR gate, and we'll try to see how it converts that particular design into layout by using Microwind, by using the Verilog code, and also we'll try to design the layout manually, which we have studied in the previous lectures. So as of now, this lecture is done up to as per this particular class. I hope you all have understood how to work upon this one particular lecture. Is it clear, everyone?
Yes, sir.
I hope now you can download that particular software and you can work upon the software. Okay.